Welcome all. This is a re-recording of the lecture on randomness, dynamics and risk that I originally presented on January 29, 2014 here at Imperial College London. It's a lecture where I try to clarify the aspects of randomness that affect our daily life, but also current science, and trying to clarify what kind of progress were reached in the overall modeling of randomness in a variety of sciences and disciplines, and also how randomness evolves in time, hence the word dynamics in the title, and finally how we can model and shape randomness through mathematics to manage our daily lives, solve our problems in science, and again social sciences, physical sciences, and so on. So randomness, dynamics, and risk. I would like to start maybe from pointing out what randomness could be in an initial interpretation of our understanding. For example, you have randomness in everyday life. As I said, we can't predict much of what happens to us. Even in science, we can have the incapability to model or calculate phenomena properly in physics, in meteorology, in a number of areas. And we can also have difficulties, however, when we try to reason on this and pinpoint to a truly random ingredient in our science, in current science, it may be very difficult to find it. So what is really the fundamental engine of randomness? What is really causing randomness in all these phenomena that affect our lives and our science, but on which we are not sure? And even if there is a variety of interpretation for the true source of randomness and the meaning of probability, as we'll see in a minute, the mathematics describing randomness is quite agreed upon, almost universally. And that's part of what we'll discuss in this lecture. The probability theory, probabilities is a quantity we assign to randomness to be able to analyze it numerically and mathematically. So probability has a variety of interpretation. Historically, it has been considered as a degree of entailment, which is the logical interpretation that goes back to Keynes, but many others as well. It has been also characterized as the degree of belief of an individual on a given event or a series of events, and this is the subjective interpretation that is due jointly to Definetti and Ramsey. And we have also frequency interpretation, which was pioneered by von Mises and again others, and a propensity interpretation by Popper. According to these different interpretations, probability is, something quite different. It's an opinion. It's the relative frequency in an objective repetition of events, and so it can be very, very different in nature. But despite the different interpretations, as I said earlier, there is almost universal agreement on the axioms the mathematics of probability should follow. And these have been written down by Kolmogorov in 1933, with one important exception we'll see later during the presentation. And as I hinted at when talking about the title of this presentation, we have also the dynamics of randomness in time. So randomness evolves in time, and when you talk about the evolution of randomness and of probabilities describing it, you have the domain of stochastic analysis. So this word stochastic, you may have heard before, describes the evolution in time of randomness. So it's randomness and time together. Randomness is difficult to grasp initially, but I can give you an example of a typical object of stochastic analysis describing the evolution of randomness in time. So this is, for example, a stochastic differential equation. That sounds a little bit scary, but the idea is actually quite simple. You have the change in a quantity, so to understand it in a precise context, suppose this is the price of some shares in the market, a stock price, okay? The equation describes the change of the price of the shares as a function of where the shares are now, okay? And it gives a local growth, a trend, which is at the rate r in this example, And then it has a second term, which is on the right-hand side, sigma x dw, which is the random term. It's a term describing instant by instant the randomness that is pumped into the system, basically, and in the stock price model in this example. So this sigma parameter, which is the amplitude of the randomness, and in financial terms, for example, is known as volatility, can be used to insert more or less randomness in the system, depending on whether the market is displaying more or less uncertainty. Okay, I can show you an example now to fix ideas. Suppose we have, like the blue equation on top, a local growth trend in the financial variable of 5%, and we have a 0.1 or 10%, if you like, volatility in the random part, with the stock price starting initially from 100. A second equation you see in green on the top describes the same signal but without any randomness. So there is no random effect, and the evolution is completely known in time with a 5% growth trend. So if we start from 100, as you see now on the plot, and we take a first random step, the equation gives us several different colored scenarios, with the green scenario being the trend, the 5% trend, and all the other scenarios being different random paths that depend on the specific random occurrence of the process we are using. And if you go on with evolution, you see randomness keeps evolving with the different scenarios in time. And you can see actually that these scenarios develop more and more, reaching, in this specific example, the final state over 1 year. Okay, now we have reached 1 year with all the colored paths which represent different scenarios. And we can also draw a probability distribution, this red bell shape curve that describes the scenarios at the final time in 1 year. So to have scenarios on the top of the scale where the bell is quite flat, that has a small probability. Scenarios in the middle part where the bell goes up have higher probability. And scenarios on the lower part where the bell goes down again is again events with small probability. So you can shape a model probability and describe it quite precisely using these dynamics and the probability law in red you see over 1 year. And you can also use, let me show you now, the different volatility values of 10% on the left-hand side graph and of 4% on the right-hand side graph to give different amounts of randomness to the system. So clearly the left-hand side graph describes a more random situation where you have more widespread randomness, whereas the right-hand side graph shows some randomness that is more concentrated around the trend of 5%, the green line, at the terminal time. You see that the red bell is much more concentrated with 4% volatility than it is with 10%. So having said this, we have described a basic tool of stochastic analysis. Now you can ask yourself, are the equations used in physical laws like this? If you think about one of the most well-known and famous physical laws, the Newton's second laws, this is not like that really. It's more like the green equation where there is no randomness, just a trend, than the other equation with all the colored scenarios. So what is Newton's law telling us? It's telling us that force is equal mass times acceleration. But mass is a constant in this theory. Acceleration is the second order change or variation in position. So you can write it as a differential equation I now put in this slide. The second variation in the position is a function, a force, of the specific position where you are. Now, you may not know the details about this type of equation, but for this lecture, all you need to understand, it's like the green equation we have seen previously, with just one trajectory. There is no random term like the W we have seen before in this equation. So because there is no random term, you could, in principle, for every single particle in the universe, if you solve this equation, you could completely predict its future. You would have to know the current position of the particle and its initial velocity, and you would have to know the precise force affecting it. But if you know that, you know, you can, if you're strong enough in calculations, you can compute the whole evolution of the universe. In this view of the universe, everything is a particle. Your body is made of particle. Your brain is made of particle. You know, your actions are the results of the forces on particles. And then solving Newton laws for all the particles of your body, of everyone else's body, of all the natural objects, you can predict completely the future of the universe. So this is something quite clearly advanced in principle to do. It's impossible to have that computational ability even with laws as simple as Newton's. So this is not feasible in practice, but in principle an entity that is strong enough, as Laplace said, to do this calculation could predict the future completely. And so this raises important questions on free will, for example. So it's not that we're talking about a mathematical theory or an ingredient of a mathematical theory like randomness that has no important consequences even on our understanding of life and human decision making and so on. This affects that all. So let's move to the next slide now that tries to see if we can recover some random behavior from particular systems. This is another example which is actually from chaos theory, showing you a very simple system where the change between time t and time t plus 1, which you see on the left-hand side of the equation, is 4 times the previous positions multiplied in this way, you see in the equation, and starting from an initial condition x0. Now there is no random ingredient here, exactly like in Newton's equation. There is nothing random entering the system. But here we assume that we are a little bit uncertain, as you see now in this lower part of the slides, on the initial position of the system. This could be maybe 99.399 or 99.4 or maybe 99.401. You're not sure because you cannot measure the initial state of the system with an infinite precision. So what happens in 3 different initial conditions? So let's plot the solution of this equation in time, okay? So you start from 100, you go down as you see in this graph, then you come up again and go down again. But the 3 different solutions are the same. You cannot really see the 3 different colors in this graph because they're overlapping in a perfect way. So wherever you start from, 99.399, 99.4 or 99.401, up to 5, let's say, seconds, the system is completely the same for the 3 choices. Then we move on, and 1 more step, 2 more steps, and as you move on, you can start seeing some divergence when you approach 10 seconds. Now it's more detectable, you can see it clearly in the plot. 1 more step, and now when we reach 10 seconds, you can see clearly the 3 different colors splitting apart. But as you move on, this becomes more and more marked to a point, you see in the final part of the graph, here we go, where the 3 trajectories seem completely unrelated to each other. So even if we start with a signal that is completely overlapping in the 3 different initial conditions, at the end here, the trajectory seems to be quite random. So there is something in the dynamics itself, even if we don't pump randomness explicitly in the system, there is something in the dynamics itself such that if you start from slightly different initial points, not exactly 100, but something very close, the future trajectory can go in a completely different direction. This is called sensitivity to initial condition, and it's chaos. It's a characteristic of deterministic systems. Again, there is no randomness here, okay? That seems to mimic randomness in some cases. Now, however, the objection we have done before to free will still stands. In principle, if you could measure the initial position of the system with infinite precision, and if in principle you could do the calculations, you would still be able to predict the system, Newton's law and physical laws like that perfectly well. You could know the future exactly, like you would be sort of omniscient. So is there anything else we can introduce in nature that is more than just sensitivity to initial conditions, as we have seen. So if nature were really truly random, then we would have a way to avoid the complete predictability of the future, even in principle. So we could ask then if this randomness exists, and if randomness is just our ignorance. And in most mathematical models in engineering, social sciences, this is the way randomness is used. Systems have a precise a configuration, but we're not good enough to measure it initially or to compute the motion in the equation. The classical example is dice throw. When you throw a dice, you don't really measure the initial force you're applying, the initial impulse, the air resistance, the mechanical equation describing, the motion of the dice. You don't really do this kind of calculations. You just throw the dice and assume that the outcome is random. But if you actually did the measurements and the calculations, you could predict where the dice is landing, on which number you're going to get. We don't do this because there's no point when you throw a dice, really. You just want to simulate a random event. So there's literature showing that throwing a dice is not really a random event. And so if you describe a dice as a random event, this is just to model your ignorance. It's not just a real physical objective randomness there. The other example is what we have seen in the example of the financial stock. You see, for example, take the FTSE 100. The FTSE 100 evolution in time is determined by a lot of factors: macroeconomic effects, government policies, market participant behavior, single behavior, and so on. If you were able to model all such effects, properly, you would then write a huge system of equations trying to describe precisely the evolution of this index. But in fact, it's too difficult and too complicated, and what you do then, you group all this complexity into a random term. And you say, this dw you see in the final equation here, the random term affecting the system, is grouping all this complexity and effects that I don't know really how to model precisely, and I hope that I am shaping the randomness in a way that accounts for these effects in a proper way. Statistical mechanics is another example of this non-fundamental objective randomness. You have systems of many particles really in a gas or in another physical situation where you cannot really measure precisely the initial positions of the different particles. There's also the uncertainty principle of quantum mechanics, of course, but I'm not talking about that yet. So you have all these different particles you can't measure precisely in the beginning, and you have too many of them to do the calculations properly. Okay? So what you do, because you're incapable of doing the calculation, you resort to a statistical description. But the statistical description is a tool to describe your ignorance, not really a fundamental effect due to a fundamental randomness in the system. And again, I'm not talking about quantum theory here. It's classical statistical mechanics. So we know that temperature, pressure, heat capacity, and the entropy arrow of time, all these aspects of systems come out of the statistical description, but they don't have a fundamental explanation in terms of fundamental laws of nature. So this is an important problem for physics as well. Well, the only one exception known to science currently where randomness is a true objective feature of the system and not something we use to describe our incapability or our ignorance or impossibility to measure things properly, is quantum mechanics. Now, this is not universally agreed upon, even this. There are interpretations of quantum theory that are deterministic, without randomness. So, for example, the pilot wave theory, which is a global hidden variable, there is ignorance, but this ignorance is referring to objects connected in a global way in ways that would not be compatible in a number of senses with the speed of light. But I'm not, again, going into details here. I think what's interesting to look at is this quantum theory where randomness finally could not just be the result of our ignorance, but an objective feature of reality. So let's see why there are mainstream interpretations of quantum theory that think that the universe is truly random at the fundamental objective level. And the way to look at this is an experiment that is called a double slit experiment. And this version I'm showing you is the version by John Bell, the famous physicist of Bell's inequality. So what we have is an electron gun. This looks like an exoteric device, but it's actually like an old TV set. You see, pre-plasma screens and LCD screens, flat screens, we had glass screens where electron used to be shoot. This is an old style TV, basically. The way it works, there is an electrical current going through a wire in the red wire you see on the left hand side, which is emitting electrons. There is an electric field. These electrons may go to a first hole, is the hole in the inner blue cage you see, it's a metal screen. Electron going through the first hole, then go through a second metal screen, the outer blue line you see here, where there are two holes, hole 2 and hole 3. And eventually, leaving the two cages, electrons may hit the glass screen you see on the right hand side. You're seeing the screen from the side here. So the first thing we do in this experiment is close the third hole. So we only have one hole in the inner cage and then a second hole in the outer metal cage, metal screen. And then there is, as I said, the glass screen. I'll now turn the picture and you will see the screen from the front. Okay? So we start shooting electrons one by one. One electron is the screen on a precise location and we mark it in red. We shoot a second electron and this hits again the screen in a second location. You can see here in the picture in red again. Third electron, fourth electron, and we go on shooting electrons one by one to the hole. Okay? After a while we get this outcome. This is actually an interesting outcome, but it's something you expect. You shoot electrons one by one through a hole, then another hole in the external cage, and they hit the screen in a sort of circular area. Okay? Let's look at this again. So this is the electrons going through the first hole, hole 1, then hole 2, and then hitting the screen in a sort of circular area, as you expect from sort of particles going through a hole. Okay, the fact that they describe a circular area, as you have seen, it can flare here or there in different positions. You can compute the probability of these positions. So the probability of an electron flaring right there in that area you have, but you cannot predict the next electron where exactly it's going to hit the screen. That's why it's considered to be random. Okay, so if it stopped here, we could say, fine, maybe there is an underlying theory of the exact position of the electron, but we're not good enough to do the calculations or to measure initial position and momentum, which is impossible, we know, in quantum theory. So we resort to an ignorance interpretation of the real position of the electron. The problem is this doesn't work in quantum theory because as we open the second hole, now we'll see something similar, but when we all open both holes together, things go really strange. So let's first open just the second hole here downstairs, hole 3, and close the hole on top, hole 2, in the outer screen, metal screen. We start shooting electrons again. I'll not go through the picture one by one, but I'll tell you that you get exactly what you expect. You have a second disk of flares in the lower part of the screen now, because this is the second hole that we open, and this is okay. So now let's open finally both holes 2 and 3 in the outer screen. Now we're here, we have both holes open outside in the outer screen and also of course the open hole in the inner screen. What do we see when we shoot electrons one by one? What you would expect from the particle nature we have seen so far of the localized flares on the screen is this. 1 electron, 2 electrons, 3 electrons, 4, 5, 6, 7, 8, and so on. You expect to see 2 disks one on the upper part of the screen where there is the hole 2 open, one on the lower part of the screen where there is hole 3 open, and they partly overlap in the part where the two holes overlap through the passage. That's what you expect. But is this what you get? No, this is not what you get. What you get is something else. Let's have a look. You start shooting electrons with both holes open now, okay? First electron, second electron, third electron, fourth electron, fifth, sixth, seventh, eighth, 9, 10, 11, 12, 13, 14, 15, and so on. So what we get in the end is a quite different picture from what we expect. You see, there are areas without any electron, the two white stripes you see in the middle, and there are areas with quite a lot of electrons and areas with less electrons. So this is typically an interference pattern. It's something that happens with waves, but not with particles, okay? Particles should behave in the classic way we have seen before. Two disks partly overlapping in the middle part. But this is not particles, this looks like waves. But remember, we're shooting the electrons one by one through the holes. So they either flare here, or flare there, or flare in the middle sometimes when the hole goes down. But how come they to intersect if we are shooting them one by one? What are they intersecting with? So in a way, you see, this slide summarizes what's going on. On the top is what you expect from the particle nature of the electron, but on the bottom is what the actual experiment shows. So when you have one hole closed, you get a disk, which is a particle behavior. But when you get both holes open, you get an interference, which is a wave behavior. So this is the famous particle-wave duality. Some theory try to solve this by assuming there is particle and waves together, so the electrons are riding waves when they move, but this is not the mainstream interpretation of quantum theory in physics. And so the question is, we have interference, yes, but interference, as I said, of what? Since the electrons are going on one by one, and with what? Waves. It's not clear. And, we can, as I said, have the probability of an electron at a given area in the screen, but we cannot predict where it will hit the screen. So this is random, but it's more than just there's all random theories, I said, because probability seems to interfere, actually, which is something new. Before quantum theory, we didn't have any kind of system that behaved like that. And the mathematical behavior of probabilities in this theory is described by the axioms of quantum theory, or von Neumann wrote them down quite precisely, but it's basically known also as Born rule, from Max Born, who wrote down the rule to compute probabilities first. And the theory has been coming out exactly in the same years as Kolmogorov, in the 30s, but it hasn't gained as much attention among mathematicians. Kolmogorov axioms are much more used, actually. It's not possible to interpret quantum theory results, as we have seen in this experiment, as ignorance interpretation again. So I cannot say the electron has a defined position in the screen. It's just that I don't know which it is. So I'm using a random model. That's not what we are doing here. According to the mainstream interpretations, it's an objective, undefined state before we actually measure it on the screen. So there's no definite position of the electron before we have the measurement on the screen. If you insist in using an ignorance or hidden variable interpretation, only global hidden variables, somehow at odds with the limited speed of light, are available. There is a sort of entanglement spreading through the universe in this other interpretation, which is non-local. So everything is instantaneously connected in a way, in ways that the theory of relativity doesn't really, model. All right, so it looks like the electron, as I said, is going to both slits as a wave. It's a strange true type of randomness where quantities do not have a defined and unknown position before measurement. It's really not defined. There is no definite status of the position of the system before we actually measure it. Is this what an extreme form of randomness would always look like? A true, there is no even definite position of anything, or configuration, let's say, of anything until we actually measure it in some way. The puzzling feature of this is actually that if you place a detector near one of the two holes in the two holes experiment, you know what happens? Let's look at this next slide. With a detector in the third hole, for example, in the lower hole in the outer screen, you get the left-hand side plot, what you expect from particles. So the interference disappears, which is strange because how do the electrons that go through the upper hole, there is no detector there, okay? How do those electrons know that there is a detector in the lower hole, so that they overall produce a pattern which is perfectly consistent with the particle interpretation. But if you switch off the detector in the third hole, you get back the interference pattern. So the very act of looking at one of the two holes influences also the electrons going through the other one. And there's variants of this experiment that really are even more puzzling, delayed choice experiments and so on. I won't go into that, but I hope you realize by now how puzzling this simple experiment is. And this has been also, made even more extreme in a way by the famous Schrödinger's cat thought experiment. Because objects don't have a precise configuration, a defined configuration before we measure them, why don't we make an experiment like this? We have a cat in a box with a radioactive decay possibly happening with a probability of 50%, okay? But according to the theory we just described, there is no definite state, decay or non-decay, before we actually make a measurement from outside the box. So what happens is, this decay could trigger a switch that opens an anesthetic gas bottle. It's the blue scenario in the picture. You see, if there is decay, the switch clicks, the blue cover goes up in the bottle, and then the gas spreads through the box, and the cat falls asleep, like in the blue scenario. However, if there is no decay, which has, again, 50% probability, the bottle stays closed, and the cat remains awakened. Now, because it's actually not defined the state of the decay prior to external measurement, at the same time, the state of the gas cover, bottle cover, is not defined, and the cat status is not defined. So the cat must be both asleep and awakened at the same time, which with daily understanding of events, daily life, to us, it looks like completely nonsensical, right? And in the famous, of course, experiment, this was a bit more extreme. The cat would be dead because there would be a poison in the bottle. But I don't want to sound harsh to cats, so I replaced that with an anesthetic. But basically, the gist of the experiment is clear. You would have a macroscopic object, animal actually, like a cat, in a superposition of states, alive and dead, at the same time, until you make an actual measurement, which looks really absurd from a macroscopic perspective, right? We don't experience these kind of things in life. Of course, there are several answers to the Schrödinger experiment, but this can really give you nightmares. Some cats are quite angry about these experiments, and you can always say it's Schrödinger's fault, really. But you have to be really careful in understanding what a measurement could be. And actually what this points out is the fact that in the mainstream interpretations of quantum theory, the measurement is not really well defined, okay? And so the notion of probability is partly affected by this. But why did I spend part of this inaugural lecture, of this lecture actually, on quantum theory? The reason is because there is, as I said, quantum theory as the only possible source of objective randomness currently known to science. We have talked about entanglement on locality as well, which is, you could preserve the ignorance interpretation of randomness. So there are definite positions, but we don't know them, we don't know how to calculate them and so on. But this is, not the mainstream interpretation. But the main point I wanted to make is that the quantum mechanic probability axioms, as I said, are different in a mathematical sense from the Kolmogorov axioms that most of science uses when dealing with randomness, probability, and stochastic processes. So what I said in the beginning is that almost everyone agrees in science on the maths of probability, even if we don't agree on what probability means, and on the meaning and on what randomness is. We agree on the maths. Well, almost universally, because quantum probability is an important field of probability that is not consistent with Kolmogorov axioms. There are a number of mathematical aspects of quantum probability that are at odds with the mainstream theory of Kolmogorov. Okay, I can just quickly mention a couple of ones. So probabilities, for example, in quantum probability are not subadditive. So the probability of A or B, an event A or another event B, is not can be larger actually than the sum of the probability of the two events, which is not allowed, in classical probability. The probability of having one event or the other in classical probability is always smaller or equal than the sum of the two probabilities. So there's a number of things that don't work with quantum probability, and it's a different mathematical theory. This is what I wanted to point out of probability. So we don't have even a universal agreement in the end on how the mathematics of probability and stochastic processes and randomness, if you like, in time should look like. But apart from this quantum probability, which is still, there's a lot of work to do, I think, on the interpretation of quantum theory, and it's still evolving as a research area. There's many world interpretations, as you certainly have heard of. There's a decoherence that plays a key role. There's a GRW theory, an advanced action theory. There's several different versions, so we don't go there now. But I wanted to point out the probability calculus that is different from what almost everyone uses, the Kolmogorov one. But once we have done that, I'll move back to Kolmogorov, and in particular now we'll look at probability and stochastic analysis in social sciences, where we go back to a hidden variables ignorance interpretation. So systems do have a defined configuration or state. The economy has a defined state, will have a defined state in the future, but I'm not good enough to measure it perfectly or to calculate it. Okay, so I will use randomness as a sort of a shortcut to model all these complexities in a mathematical way. So let me start then by one of the areas where stochastic analysis and randomness has been used mostly and often in a very controversial way. So I'm referring to the option and derivatives market. That, this is a very important market that reached in June 2011, according to the Bank of International Settlements, an overall outstanding notional of $708 trillion. Okay, so it's a huge amount of money if you think about it. It's if you remember that the total gross domestic product of the planet on the same year was 79 trillions, and the total gross domestic product of the US, for example, in the same year was 15 trillion. Here we're talking about 708. Okay, trillion, you need exponential notation to make sense of that, 10 to the 14, otherwise you really get lost in counting zeros. So it's a huge number, but it's almost 10 times the gross domestic product of the planet. So what does this mean? There is double counting clearly in outstanding notional, but outstanding notional is the nominal amount on which you write a derivative contract. It's the money backing, in a sense, a derivative trade. It's true that two opposite trades may cancel each other, so that's why you're double counting here. But even discounting that, this notional amount is amazing. You know, thinking that you have derivative financial contracts written on a total amount that is 10 times the planet economic output is amazing, at least to me. So who started this? And actually we see a familiar figure here. It's Thales, who is considered to be the father of philosophy, the father of science as well, modern science by many. And now we're also finding out is the father of derivative trading. So he really has a lot to answer for. And actually in 580 before Christ, what he did, he optioned the use of olive presses because he had predicted that the olive crop would be fantastic on that year due to meteorology and a number of factors. So, you know, the future, of course, olive crop is random, but he made an assessment and then he bought the rights to use the olive presses. And when people would need the olive presses in the future, they would have to pay him a given amount. And he made a lot of money like that. So this is a philosopher, scientist, entrepreneur. It looks like really a fantastic figure if you think about it in many respects. But later, of course, the theory was improved and made into modern mainstream social sciences by a number of players, including Bachelier and Definetti and Ramsey in a way, and also, most importantly, Black-Scholes and Merton in 1973, which led to the Nobel Award for Scholes and Merton. Black had passed away earlier. So let's look at this, what the social sciences application, the derivatives actually deal with. So I'll give you an example of a simple financial product, which is an option, a call option, which allows you to gamble on the growth of a financial asset, let's say a stock again, okay, over a given time horizon, 1 year in the future in this picture. You start from a red value from the stock, which you see on the graph, which is called S0, and this may grow up a lot randomly. It's the blue scenario you see where you win a lot. It may grow up a little bit, the brown scenario when you win a little, or it may even go down, and it's the green scenario. The way this gamble is designed, you win if the asset grows up, but you don't lose anything if it goes down. So this gamble pays you the 1 year growth with respect to the initial value, or nothing if it goes down. So you don't lose anything. You can only win or draw if it stays the same. Clearly, if you go to a bank and buy a gamble like that, the bank is going to charge you because you can only win or draw, so it's not going to be like the bank gives this to you for free. But then what is the correct price of this gamble? You should pay to the bank in order to be able to enter into this actually. And the correct price of this gamble is an option price, and this is the theory of valuation of financial contracts and derivatives more generally. So let's then move to see in another picture how this would look like. And you have an equation like the stochastic differential equation we have seen earlier, describing the evolution of the underlying asset for the gamble up to 1 year, okay? And then remember, if it has gone up, you win the difference. If it goes down, nothing happens. You don't lose. So how much should you pay initially to the bank to be given this opportunity to gamble? And you have two equations here, and you're not really seeing double. And we'll see why you have two equations in a second. But let's have a look at what the theory is telling us, okay? So basically, the Black and Scholes theory, which led to the Nobel Award, and Merton was also contributing to it importantly, is saying that the unique price is the expected value over 1 year. So under this red distribution of probabilities you see on the right hand side, you have to average the growth of the asset with respect to the initial time over the final probability distribution. So you take the average of the growth with respect to 100 according to the red distribution coming from the scenarios you evolved with the equation for the asset, the stochastic differential equation. But what the theory is actually telling you is that in doing this, you don't use the probability distribution under a probability measure, which is the real one, where you measure statistically the behavior of the assets. You look at the history, you run some historical statistical analysis, and you come up with the behavior of the stochastic differential equation. This is not what you do according to the theory. According to the theory, you price this gamble using a different probability measure called Q. That's what you see in the second equation, where the local trend or growth of the stock on which you are gambling is a risk-free rate. So it's a rate of growth for a risk-free investment. Okay? It's typically a bank account of a very solid bank or a government bond of a very solid economy. You might ask what that is these days. Okay, it's a legitimate question, but let's say that we have a benchmark for a risk-free investment. Then the theory is saying take the expected value of your future outcome under, however, in a world where the local growth of the asset is the risk-free rate. So in a way, this is amazing because you're gambling on the growth of a stock over 1 year, but the price of this growth of this gamble does not depend on the local trend or growth of your underlying stock. And you may say, what? I'm gambling on the overall 1 year growth, and the price of this gamble does not depend on the local growth in the trend? That is very strange, isn't it? And this is an amazing result in many ways. The first time you hear it, you even doubt it. But the reason is it's possible to design what is called an hedging strategy that allows you to replicate exactly the risk of the contract. And when you look at with a self-financing strategy that doesn't cost you anything except the initial, resources needed to set it up. And then with the initial value of the overall strategy is the price of the option. And this turns out not to depend on the real local growth of the asset, but only on the risk-free investment benchmark. So it's like in this plot here with the 3 colors again, where you have an optimistic investor who thinks that the real growth of the underlying asset is 10% on trend. You have the blue investor who is very pessimistic, who thinks that the growth should be minus 4%, so it's a loss actually, it's going down. But what the theory is telling you is that whether you are optimistic or pessimistic, there is an objective price for this gamble, which is the price the bank will ask you to enter this gamble, and it's according to the green scenarios, where the growth locally is at the risk-free trend, in this example of 5%, but now these days risk-free rates are actually much lower. I took a relatively large value to give it some visible trend. Okay, so then your individual perception or your individual statistical analysis of the growth of the asset does not impact the cost on the gamble over 1 year on the growth itself, which is a very counterintuitive result in a way. The volatility, which determines the amount of randomness, yes, by all means, that's a fundamental ingredient of the price the bank will charge you, but not the real trend of the asset. It's really counterintuitive, as I said, and it's contributed to generate very large derivative markets to the point of 708 trillion notional I mentioned earlier. And the reason is the price of such a contract does not depend on the local trend of an asset. And the local trend of assets is the most difficult thing to know, because if I knew the local trend of stocks, I would be a billionaire, okay? And clearly, a theory which tells you that to price financial products, you don't need to know this very difficult parameter, which is very hard to estimate, is giving to the price of derivative objects an objectivity that they wouldn't have if the price did depend on the real local trend. And this is a picture of Scholes and Merton getting the Nobel Prize in 1997, but it's also a cautionary tale, because on the right-hand side you see the progression of the long-term capital management fund. It's an hedge fund in the US that in 1998, 1 year later after the Nobel Award, crashed basically and had to be rescued by the US government, the Federal Reserve. The problem is that the two scientists, Merton and Scholes, who were in the Nobel awarded ceremony and who got the Nobel Award, were also on the board of this hedge fund. So that doesn't mean that they're of course responsible for this. I'm not saying anything of sorts, but it means that even with the people who created the modern version of this theory, you have to be very careful. They can be in the board of your hedge fund, and yet there might be some risks that you have not modeled properly, or some assumptions in your theory that are not accurate. So this leads me to describe the financial crisis. There's been a number of crises clearly after 73. The market players, started introducing derivative on a number of areas, both more complex than the simple gamble we have seen on the growth. There are derivatives that look at very different aspects, barrier events, the whole history of the underlying stock, more than one stock, default events, foreign exchange variables, interest rates, even population longevity, earthquakes, weather derivatives. You can actually write financial product, the market wrote financial products on every sort of variable. And sometimes in areas where the original assumptions of the Black-Scholes theory would not hold clearly, And this has gone on for quite some time. The theory has been extrapolated often beyond the natural limit of the theory. And I have done a lot of work over the years to analyze the limits of the theory and to propose extensions that would account for what was not really included in the original setup. I'm giving a few examples right now. The first one is the continuous time theory. Now, the reason why we use continuous time is because we have differential equations, which are very important mathematical tools to describe the evolution of a system, even a financial system. But is time in trading really continuous? We know that traders actually act in discrete time, there's no real continuous time in the end. And if you take a discrete time grid with the time step you choose a priori, it can be very small, 1 billionth of a second, 1 millisecond, 1 minute. You may choose yourself the time step on the trading grid. And then you can have two different random models for the stock you're trading in the option. On the left-hand side, you have a model with a local growth M and a volatility sigma. On the right-hand side, you have a different stock model with the trend mu and a volatility V. Okay? You can define the trend mu in the right-hand side equation such that the two systems are completely indistinguishable by historical statistical estimation. So if you do your estimation on the trading grid in the past and you reach now, there's no way you can distinguish in the physical real measure, probability measure, these two models. However, they imply very different option prices, so different that they can span the whole range of possible prices for the gamble, the option. So you have two indistinguishable models in a very thin discrete time grid that imply completely different option prices. So are we justified in assuming a continuous time in a world where the time is discrete, if there can be such a difference in the option prices, given two equivalent models in historical observations. This is an important question that we investigated. And also another point that I would mention is the stochastic differential equation in the examples I showed you earlier for the stock evolution in time was very simple. There was a trend you see on top of this equation, which is proportional to a rate r, the risk-free rate we have seen, and there is a volatility parameter sigma, which tells you the amount of randomness you have in the system. But can we use more rich and complex equations than this? We indeed can, and you see in the second line here an equation where the volatility v is a function of where the stock is and not just a constant or a deterministic curve. It's a function of where the stock is in each different scenario, and this can be shaped such that the stock has a distribution which is a mixture of distributions. And you see, when you run the different scenarios now, you have more extreme possibilities in the behavior of the stock, and you see you have a red final probability distribution you see on the right hand side generated by all these scenarios with this new equation, and you can see a hump on the lower part of the plot. Okay, so very low values of the stock now become more likely due to that hump, and the model can produce riskier situation actually than the previous original Black-Scholes model can produce. And this is important to have your model, to give your model the capability of having more risk than the standard Black-Scholes Merton model would allow you to have. And that's how the market behaved many times actually. One other aspect that is interesting to briefly mention is the theory of interest rates. So when you model a single stock price or an exchange rate, you model one variable. But when you model an interest rate curve, you model a whole curve. You need to model how the interest rate over 1 month evolves, over 3 months, over 1 year, 1 year and a half. You may even go up to 20, 30 years if you have long-term interest rates. But you need to model this whole curve. So now this moves as a curve, not as a single point. And a theory is a theory then of how an infinite dimensional object, which is a whole curve, evolves in time. You see here a very simple example of the initial curve on the left-hand side, going up in a number of different scenario of curves over 1 year, the different colors, and then in 4 years you have another set of scenarios on the here upper part of the graph. Now this is a very simple, almost parallel shift of the curve, even if it gets flatter you see in the later scenarios, but generally the curve can move in much more complex ways, and you have to write the dynamics of an infinite dimensional random object, which is quite challenging, and I did a lot of work in interest rate theory as well. And finally, maybe the part of my research that is more related to the mainstream events following the crisis started in 2007 is the modeling of credit risk and default modeling in particular. You trade with entities, other banks, corporate clients, and financial institutions and so on, who may however experience a default event. So if you are expecting payments from another party and the party defaults, you're not going to receive that payment and you face a loss. So this was one of the important risks that we witnessed in 2007 and 2008. In 2007 we had the mortgage crisis in the US, and then in 2008 the situation started to spread with basically a number of defaults, acting on the happening in the financial industry. Lehman Brothers is one of the most famous events, but there were others actually. And the industry models for default, and especially the way the different defaults of names are interconnected, was a simplistic model. It has been a model that has been there for some time, but it's static. There is no real dynamics or evolution of the dependent structure across different defaults of different entities. there is no volatility in the credit quality of single entities in the model that was used in many cases. There's an inconsistent model in many ways that may even imply that the defaulted company resurrects later, you see, which is an unacceptable assumption when you're modeling default events for counterparty risk, for example. And what I did there, I introduced a dynamic, really dynamic model for losses and dependence in the financial sector, and not only there, where you can see a complex evolution consistent with market data. So I can show you actually this was collected in this book called Credit Models and the Crisis. You can see the loss distribution. This is a probability distribution for how much you can lose in your portfolio. It's coming from a collateralized debt obligation, a so-called CDO, but that doesn't matter. It's telling you that after 3 years, your loss distribution is this. Basically, for example, this hump gives you the probability of losing around 3%, slightly more than 2% here, of your portfolio. And as you move in time, this is the blue one is the loss in 3 years, but then the green one, you see, is the loss, the dotted curve in 5 years, and the red dotted curve is in 7 years. So as you see, the loss spreads to the right because it can only increase in time due to more and more defaults in your portfolio. And it's, however, quite structured. You see there are humps, multiple humps already in the 3-year loss, in the blue curve, meaning that the risk can be quite localized in sectors and not very smooth as the previous industry models were sort of assuming. And if you look at the tail of the distribution, and we'll see a move in a minute, you can see that there is now, in the red plot, for example, you can see clearly between 15 and 20%, there is a quite marked loss probability hump in this plot. And if you go to the final one, you can see the tail where 75% of the portfolio in 7 years can be lost in an extreme, almost Armageddon event, because this is the portfolio, by the way, of the 125 most liquid credit names in Europe. So if 80% of those names default, we're really looking at a catastrophic event in the market. Admittedly, this probability is low because if you look at the scale on the axis, that's quite small. But it's still quite marked. There is a systemic event risk that the previous models couldn't capture. And this model is also fully consistent with market data. And I can show you now a quick movie of how this looks like in an animated way through the crisis. Okay, so now we're going to see a movie that shows you how the probability distribution of the losses I just showed previously evolves exactly in time. So we're running from 2005 to 2007 and later to see how, the subprime crisis, for example, affected the implied loss distribution coming from the CDO products and the iTraxx in particular. So we can start observing, you see the big part of the loss is on the left-hand side, meaning that there is no loss with a high probability. The names are, after all, quite safe, 125 most liquid credit names. Then there is a quite marked mode, around 20% of the probability loss of the loss. So there is a marked probability of having a 20% loss when there isn't here, for example, on the left-hand side of 20, any probability, except if you go to near zero. So there is quite a marked cluster of probability around 20% that you can keep seeing. But now we move to the right-hand side to a much later date. So we're still 2006, you see, and the situation does not change much. You can see a little bit of motion on the right tail of this probability low, but not much, okay? How we move to 2007, actually, I'm letting the movie run in a way. We're now in March. We're approaching April. Remember, the subprime crisis started in summer, so we're looking at July, August. That's why I joined London. I've been quite lucky, actually, in a way. And you see now the modes move a lot. This grows, and on the right hand side, look at the extreme part towards 125, which, remember, it's a portfolio of 125 names. We can see quite clearly the modes, they're becoming more and more visible. Big modes in the tail, meaning that big losses now become possible with high probability. The Armageddon event on the CDO is given a non-zero probability by the market, okay? And as we are reaching the end, we are now in 2008, there's the default of Lehman. Clearly, you see a quite marked right and part of the distribution here go spiking up, really. And then the graph stops, basically the movie stops, but you have seen how the nature of randomness modeled by a probability distribution has an important dynamics that often the model used in the industry for credit risk do not actually capture. So this has been, this is important, and we can actually think this is one of the lessons we have learned from the financial crisis. But it's important also to point out, I was doing this before the 2007 event. I was doing this in 2005 and 2006 for the dynamics. These plots you have seen are from a model that we wrote in 2006 and implemented in 2006. Now, the other parts of the financial situation that follow the crisis I would like to describe and related again to my research concern the valuation adjustments. So the valuation adjustments are something that came up when the market realized that classic theory of Black-Scholes was not really suited to valuation anymore. So for example, the basic theory of Black-Scholes assumes there is no credit risk, no default, as I said earlier, but in 1 month of 2008, we had 8 financial events, defaults. Fannie Mae, Freddie Mac, Lehman Brothers, Washington Mutual, the 3 Icelandic banks, and in a way also Merrill Lynch. It didn't actually technically default, but it was helped considerably by the merge with Bank of America following pressure from government. So overall, 8 credit events of important mainstream financial institutions in 1 month shows clearly that the assumptions of no default risk, especially for financial, is not tenable. I had worked a long time on this, much earlier than 2008 actually. And also another risk that has been showing up is liquidity risk, both in the area of trading liquidity and funding liquidity. Funding liquidity means basically that the cost of borrowing is not going to impact you in an extreme way. But we have seen that actually during the crisis, there was a problem also with funding liquidity as well. The Black-Scholes model assumes in its basic formulation that you can borrow and lend indefinitely any kind of amount at the risk-free rate, regardless of your status, your credit quality, and so on. We know this is not true, obviously, and now the effort has been incorporating also the costs of borrowing and the benefits of lending into the equations in a proper way. This may, result in some interesting mathematical problems, especially nonlinear problems. From 2002, I worked mostly on the credit valuation adjustment, which is when you try to add a term to the classical theory to account also for credit risk. And then the funding problem more recently prompted a funding valuation adjustment. But these adjustments are sort of separated, they are kept separated, but really often interact. So we need an holistic view of this, which is what I've tried to develop over the years, and more recently as well. Now that this is a relevant problem, you can see already from the financial statements of mainstream banks. So Citigroup, for example, had the benefit from the valuation adjustment for credit risk and debit valuation adjustment in this case of 2.5 billion in 2009. More recently, JP Morgan declared a loss of 1.5 billion due to funding costs in January of this year, 2014. So these are relevant problems. We're not talking about purely theoretical issues. The fundamental nonlinearities that you have due to funding costs and replacement closeout in the credit event show up in interesting mathematical objects. The theory is not linear, even for valuation, which means that if you put different financial assets in a portfolio, the total value of the portfolio is not the sum of the values of the single assets once you take into account credit risk and funding costs, the cost of collateral, and also now there is a lot of political pressure to trade through central repositories clearing houses, CCPs so-called, and this is also subject to some nonlinear effects that we have analyzed in our research actually. And sometimes this is summarized by saying this is the end of Platonic pricing, the thought that there could be a probability measure Q, as with the Q we have seen in the earlier examples with the green trend at the risk-free rate, this single probability measure that you can use to compute the price of all gambles of all financial products is not really there anymore. There is a more complex theory that depends on who is trading a specific portfolios, on the properties of the entities trading it, and of the portfolio itself. And the effect is nonlinear. You have to decide the level of aggregation of assets a priori. And the final minutes of this lecture, I would like to talk also very, very shortly about my research in signal processing and nonlinear filtering in particular. And this is again about randomness. You have a random signal, so you have a physical trajectory or some process in nature or engineering that is random. And this process is observed, but there is some noise also in the observation, some more randomness, additional randomness in the observation. So the system is random, and there is some more randomness in a way you observe it. And what you try to do is you try to estimate the exact status of the system, state of the system, given the observations, the noisy observations. This has countless applications in many industries. For example, it can be used with submarines, trajectories, spacecrafts. It has been used with spacecrafts, satellite orbits, re-entry trajectories for spacecrafts. Again, target tracking for military purposes, water level prediction to check the sea behavior, seismology, bioengineering, econometrics in economics as well. And you could try to have a consistent theory of financial modeling under the two probability measures I sketched earlier. This involves some filtering theory as well. And I see a very simple example, if you would like to write down an equation, is an equation where the signal, the objective signal, is pure randomness with a given volatility sigma, as you see in this equation. And we observe the third power. You see there is x with a 3 on top. This is the third power of the signal, plus some additional noise v, not w, but v. W is the true randomness of the system, so to speak, or maybe our ignorance on it, and v is additional noise in the observation process. Okay, and the problem is estimate the state x of the true state x of the system given observation of the process y, which is noisy. And I did an approach on filtering when the system is nonlinear, which is again an infinite dimensional problem, as we have seen, for example, with the interest rate curves. It's again an infinite dimensional problem. And I used a geometry in the structure of randomness of probability measures, actually, which are ways to measure randomness. There is a natural geometry you can use in the probability distributions that helps in this kind of process. And this helpful geometry is being used in very concrete numerical experiments. Here you see, for example, typically the true signal of the system, and actually it's actually not the true signal, is the mean of the projection filter, which is the particular filter based on geometry I introduced, and the mean of the exact filter, which is the dotted line. And as you can see, they are very, very close, meaning that we are tracking the optimal estimator in a way of the best possible filter with our geometric method. Our geometric filter is finite dimensional. Nothing infinite dimensional can be exactly implemented in a finite machine. but our filter is a finite dimensional approximation of this infinite dimensional object, and it tracks it pretty well, as you can see from the upper graph. The lower graph shows you the local error in the approximation, and it's sparkling up in some specific points, but overall it's quite low, so it's a good approximation in a number of ways, and we can track the quality of the approximation. So I was mentioning that this has been used in rocket science, so this was, you know, a lecture on the overall interpretation of probability, its mathematical use, its use with dynamics and risk in physics, in finance, but finally this is rocket science, and this is an excerpt from the Apollo 11 moon landing, where they used the Kalman filter, which is a linear filter actually, for reading the real position of the spacecraft from noisy observations coming from a number of sources. And this was used clearly in the moon landing when we had the Apollo 11 historical event in 1969. And we have reached the stars, and it could be a good, really a good place to stop, but I was actually just looking for an excuse to show this picture, which is the famous Saturn V rocket and the lunar capsule here, you see. But seriously, the lecture has been based especially on my work on social sciences that you find in a number of books and references. Some are presented here, just a summary. And I would like to really thank you for listening through this and for your kind attention. And I finally would like to mention that a quite substantial amount of references is available in the final part of the presentation for, you know, if you are interested in gaining more knowledge on some specific aspects of the presentation I did. This was a summary of years and years of research compressed into 1 hour, so clearly I left out a lot of points. In some parts have been sketchy, trying to be as rigorous as I could, as much as I could, but clearly in such a limited amount of time it's not always possible. But if you look at the final part, you will find a lot of references to go deeper in some of the areas I described. Okay, thank you very much.